Now let's discuss about the last transistor connection, the common collector connection. In the common collector circuit, the collector is made common to both input and output. The input is applied across the base collector junction of the transistor and the output is taken across the emitter collector junction of the transistor. Here the figures represent the NPN transistors and the PNP transistors. Here first diagram or the figure on the left side represents the NPN transistor with a common collector connection, and the second one, the figure on the right side, represents the PNP transistor with a common collector connection. Here the collector is made common to both input and output, and remember that if collector is made common, then base is the input terminal and the emitter is the output terminal. So the input current will be the base current and output current will be the emitter current, and the input voltage is the base collector voltage and output voltage is the emitter collector voltage. So now let's discuss about the current amplification factor in the case of a common collector transistor connection. Current amplification factor, we know that it is nothing but the ratio of the output current to the input current. So in the case of a common collector transistor connection, output current is the emitter current and input current is the base current. So the current amplification factor gamma can be defined as the ratio of the change in the emitter current to the ratio change in the base current, delta IE by delta IB. In the case of a DC sources or DC currents alone, the gamma can be written as gamma is equal to IE divided by IB. Here we know that IE is much greater than IB, so the value of gamma is always greater than 1 and it is very high. And also we have defined the current amplification factor alpha for common base connection, beta for common emitter connection, and gamma for common collector connection. And also we have seen the interrelation between the alpha and beta. Now let's have a relation between this gamma and alpha. For that I am again considering the emitter current as IE is equal to IC plus IB. That is the general expression for any transistor. Now the change in the emitter current delta IE can be written as delta IC plus delta IB. Divide this expression throughout by delta IB, then we have delta IE divided by delta IB plus delta equal to delta IC by delta IB plus 1. Now let's recall the expressions for alpha, beta and gamma. Alpha is given by delta IC divided by delta IE, and beta is given by delta IC divided by delta IB. So if you go to this expression, delta IE by delta IB, in the above equation delta IE by delta IB is gamma, so gamma is equal to delta IC by delta IB is beta, so beta plus 1. This is the one expression which relates the gamma and beta, that is the current amplification factor in common collector connection and common emitter connection. Now we know that beta is given by alpha divided by 1 minus alpha. If we use that expression, that is beta is equal to alpha divided by 1 minus alpha. This is another expression for beta in terms of alpha. If we substitute it here, we can have gamma is equal to alpha divided by 1 minus alpha plus 1, which is equal to, if you cross multiply it by 1 minus alpha, then we have alpha plus 1 minus alpha. Alpha and alpha will cancel. What remains is 1 by 1 minus alpha. So gamma is equal to 1 by 1 minus alpha. This is the relation between current amplification factor in the case of a common collector and a common base connections. So remember these two expressions. Now the expression for the collector current can be obtained as IC is equal to alpha IE plus ICBO. But IE, we know that IE is equal to IC plus IB. So IC will be equal to alpha into IC plus IB plus ICBO, or this can be rewritten in this way. Alpha IC can be taken to the LHS, so we will have 1 minus alpha. So IC is equal to alpha IB divided by 1 minus alpha plus 1 by 1 minus alpha into ICBO, or 1 minus alpha is gamma, so it is equal to, also we know that 1 minus 1 divided by 1 minus alpha is equal to gamma, so alpha can be written as, or 1 minus alpha is 1 by gamma, so alpha will be equal to 1 minus 1 by gamma, which is equal to gamma minus 1 by gamma. So if you substitute it here, we can have alpha is gamma minus 1 divided by gamma into 1 by alpha is gamma into IB plus gamma into ICBO. So which is equal to IC is equal to gamma get cancels, gamma minus 1 into IB plus gamma times ICBO. So we can rewrite that equation to here, that is the collector current IC is equal to, in terms of gamma it is gamma minus 1 into IB plus gamma times ICBO. So this is the expression for IC in terms of gamma and IB. And remember that this common collector connection has a very high input resistance and of the order of 750 kilo ohms, and have very low output resistance of the order of 50 ohms. Due to this reason, the voltage gain provided by this circuit is always less than 1. Even though there is a high current gain, since the output resistance is much higher than the input resistance, the input resistance is much higher than the output resistance, there is no voltage amplification, or voltage gain in the case of a common collector connection is less than 1. So this type of amplifier or connections, common collector connections, are seldom used for the transistor or amplification purposes. This is used for the impedance matching circuits. So the circuits or applications where we can use common collector circuit is the circuits which needs the impedance matching. Impedance means the resistance output and input resistance we need to have a if we need to drive a high source, high impedance source, we need to use these common collector connections. Then we have, so far we have discussed about all the three type of transistor connections, and let's have a comparison between these three transistor connections. So first of all, let's consider the input resistance. In the case of a common base connection, the input resistance is very low, it is of the order of 100 ohms. The common emitter, it is low but little high than common base, and it comes around 750 ohms or less than 1 kilo ohms. And in the case of a common collector connection, it is very high and it is of the order of 750 kilo ohms. And when we are considering the output resistance, the common base will have a very high output resistance of the order of 450 kilo ohms. The common emitter will have a high output resistance, but it is low when compared to the output resistance of the common base connection, but it is again of the order of few kilo ohms. It comes around 40 to 50 kilo ohms. But the common collector connection will have an output resistance of very low, and it is only of the order of 50 ohms. It all vary from 25 to 50 ohms in the case of a common collector connection. Now if we consider the important parameters, the current gain and voltage gain, the common base configuration has a voltage gain around 150, but the common emitter will have a voltage gain of 500, and common collector is not having any voltage gain. That means the voltage gain is less than 1. So the output voltage will be less than the input voltage in the case of a common collector connection, but in the case of a common emitter connection, we will get a voltage gain around 500 times than the input. Then if you consider the current gain, the common base is having a current gain of less than 1. The common emitter is again having current gain between 20 to 500. As we have seen that the current gain means the current amplification factor, it is around, the value of beta is around for 20 to, it varies from 20 to 500, and common collector is having a appreciable current gain, but there is no voltage gain. And if we consider the applications, the common base connection is used for high frequency applications, and common emitter connection is used for audio frequency applications, and the common collector connection is used for impedance matching. So that's all about the comparison between the three different transistor connections: common base, common emitter, and a common collector. And if we consider all the parameter which we have already discussed here, we can see that the common emitter and common collector will have a current gain, but the common collector does not have a voltage gain, but common base is having a voltage gain. And if we consider all these one, the gains, the current gain and voltage gain, the common emitter provides both current gain and voltage gain, hence we will have a power gain. So the power amplification we will have in the case of a common emitter transistor amplifier. And also if we consider these resistances, input and output resistances, the difference between input and output resistances in the case of a common base and common collector are very high. Very high means it is common base is having around 450 kilo ohms of difference, and common collector will have around 750 kilo ohms of difference in input and output resistances. But if we consider the common emitter transistor, it is having difference in the input and output resistance of a few kilo ohms only. That means when we need to have a multi-stage amplifiers, that means we will have more than one stage of amplifying actions. We have to connect one amplifier to the other, which is called the coupling. So common emitter transistor amplifier is suitable for the coupling of one stage to the another stage. So this common emitter will have that advantage also. So that if we can compare all the three transistor connection, the common emitter transistor connection is the most commonly used and it is the most efficient transistor connections. Out of the three, common emitter transistor connection is the most commonly used and the most efficient one. And in almost all 90 to 95% of applications we will use common emitter transistor connections. And this common emitter transistor connection will have the following advantages. One is the high current gain. It provides high current gain because we know that the collector current IC is the output current. IC is equal to beta IB plus ICEO, where ICEO is very small but beta is around 500. So beta IB will be very high value, so it will provide a high current gain. Then second reason for choosing common emitter transistor connection for most of the practical purpose is that it provides very high voltage gain and power gain. So the common emitter transistor connection will provide a high voltage gain and power gain, because it is having a very high voltage gain. Due to high current gain, the common emitter will have a high voltage gain also, because current is multiplied by the output resistance, so we will get the voltage. So output resistance is also high for a common emitter connection, so we will have high output voltage. So current and voltages are very high, so we will get a high power output in the case of common emitter transistor connection. And another thing is that I told you in the while comparing, we can see that input and output resistances are moderate. The output resistance is around 750 ohms and the input resistance is around 750 ohms and output resistance is around 45 kilo ohms. That means they are moderate, so the input and output resistances are moderate input and output resistances, which provides this transistor connection to be used for the best coupling. Coupling means one stage of the transistor amplifier can be connected to the next stage so that there is no much uh, impedance mismatching occurs when they are coupled together. So these three factors, that is high current gain, the high voltage and power gain, and moderate input and output impedance ratio or resistance, provide us this common emitter transistor connection to be used for most of the practical applications. Thank you.